Hello everyone. In this video we are going to discuss the basics of chapter real numbers. So before going to the real numbers, we need to have a clarity what exactly will be there before real numbers and how those numbers are connected to this chapter real numbers. So let's start our discussion. The first number system we will be having is natural numbers. I hope everyone has a perfect clarity about this one. Natural numbers starting from 1, 2, 3, 4, 5 and so on. And these natural numbers are represented by capital N. So in this we can see that smallest natural number is 1 and the biggest natural number does not exist. After these natural numbers we will be having whole numbers. For the natural number system, if I add 0, so 0, 1, 2, 3, 4, 5 and so on. These are called as whole numbers. These whole numbers are represented by capital W and the smallest whole number is 0. After natural numbers and whole numbers, we will be having integers. Integers are the numbers which are positive, negative, along with that 0. Integers are positive numbers, negative numbers along with 0, and these integers are represented by I or Z. Now after integers we will be having one of the important topics, that is rational numbers. The numbers which are in the form of P by Q, where P comma Q belongs to integers and Q not equals to 0. These rational numbers are represented by capital Q. So anything which is in the form of P by Q, then that's nothing but numerator and denominator. So for example 2 by 3 is a rational number, minus 1 by 7 is a rational number, and a normal number 8 is also a rational number because 8 can also be written as 8 by 1, and 0 is also a rational number because 0 also can be written as 0 by 1. And pi, if we take, I will discuss about this in the next session. Now the next one is irrational numbers. The numbers which are not rational. The numbers which are not rational are called as irrational numbers, and these irrational numbers are represented with Q dash. So now moving to our chapter, that is real numbers. Combination of rational and irrational called as real numbers. I repeat, combination of rational and irrational numbers is real numbers. Real numbers are represented with capital R. So now if you move back to this one, rational numbers. In the rational numbers we will be having two kind of decimals. One is terminating decimal and the second one is non-terminating repeating kind of decimal. Non-terminating repeating. And whereas in irrational numbers we will be having non-terminating non-repeating. So that in our words we can say that neither terminating nor repeating. In rational numbers we will be having terminating kind of decimals, non-terminating repeating decimals, whereas in irrational numbers we will be having non-terminating non-repeating, nothing but neither terminating nor repeating kind of decimals. So all these decimals together we can say that it is real numbers. Now what is the purpose of reading or studying about these real numbers? Let us check that now. Natural numbers system completely is smaller than the whole number system. This whole number system is still smaller than integers, and these integers are still smaller than rational numbers. And separately we will be having one more system, that is irrational numbers. This entirely together is real numbers. So if we say that any question will be asked in the exam from smaller circle to bigger circle, it is always a true statement. For example, is every natural number a whole number? Yes. Is every natural number an integer? Yes. Is every natural number a rational number? Yes. Is every natural number a real number? Yes. Is every whole number an integer? Yes. Is every whole number a rational number? Yes. Is every whole number a real number? Yes. Is every integer a rational number? Yes. Is every integer a real number? Yes. The same way, if the question is asked from outer circle to inner circle, always the statement is false statement. For example, is every whole number natural number? False. Is every integer a natural number? False. Is every rational number natural number? False. Is every real number natural number? False. Otherwise, is every integer a whole number? No. Is every rational number a whole number? No. Is every real number a whole number? No. The same case with this irrational also. Is every irrational is a real number? Yes. And is every real number an irrational number? No. And there is no connection between this system as well as this system. So we cannot say like, is every natural number irrational? Obviously no. Is every whole number is irrational? No, obviously. So here from this system to this system, or else from here to here, always the statement is false only. So I can say clearly that there is no relation between these all systems and this irrational number system. So now we'll moving to our original chapter, that is real numbers. Combination of rational numbers and irrational numbers is real numbers. The same thing we can write it as rational numbers combined with irrational numbers called as real numbers. This symbol means union, nothing but all together. Of course, if you did not remember the purpose, I mean main purpose of this symbol, just remember like a union all together only. So rational numbers and irrational numbers together is called as real numbers. Here we discuss what the relation is in between all the number systems with the help of a Venn diagram, right? Now let us check the same with the help of another way, that is natural numbers are smaller than whole numbers, which are smaller than integers, which are smaller than rational numbers, which are smaller than real numbers. Here this symbol means subset. In our simple words, we can speak like a less than symbol. Natural numbers are smaller than whole numbers are smaller than integers are smaller than rational numbers are smaller than real numbers. The same case we can go with irrational numbers are smaller than real numbers. So any question, if it is asked from left to right, always is true statement. For example, is every natural number a real number? Yes. Is every natural number a rational number? Yes. Is every natural number an integer? Yes. Is every whole number a real number? Yes. Any question which is asked from left side to right side is always a true statement. Whereas if the question is asked from right to left, always it is a false statement. For example, is every real number an irrational? False. Is every irrational number is real number? Yes. Now we are going to learn prime factorization. So let us take an example of number 32. Here left side, whatever you're going to write, those all numbers should be prime numbers only compulsory. So starting from the first number 2. 32 comes in 2 table. Yes. 2 times 16. Will 16 comes in 2 table? Yes. 2 times 8. Will 8 comes in 2 table? Yes. 2 4s are 8. Will 4 comes in 2 table? Yes. 2 2s are 4. And as soon as the last number is a prime number, you can stop the process there itself. So now here the last number is 2, right? It's a prime number, so we can stop the process. Now 32 is nothing but 2 into 2 into 2 into 2 into 2. So that is 32 equals to 2 into 2 into 2 into 2 into 2. Now if you multiply again, we need to get 32. 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32. So let us take one more example of 100. First prime number I am going with. So will 100 comes in 2 table? Yes. 2 times 50. Will 50 comes in 2 table? Yes. 2 times 25. Will 25 comes in 2 table? It is not coming in 2 table. So I'll move to the next prime number, that is 3. In 3 table will 25 comes? No. So I'm moving to the next prime number 5. In 5 table will 25 comes? Yes. 5 5s are 25. As this last number is a prime number itself, so we can stop the process here. Now 100 is nothing but 2 into 2 into 5 into 5. Let us take one more number. I'm going with 81. First prime number is 2. 81 is odd number, so it won't come in 2 tables. So I'm moving to the next prime number 3. 3 27 times is 81. 3 9s are 27. 3 3s are 9. As the last number is a prime number, so we can stop the process here. So 81 is nothing but 3 into 3 into 3 into 3. Now with the help of this prime factorization, we will try to find out the LCM as well as HCF of the given number. So let us check how to solve it. The next topic which we are going to discuss is LCM and HCF by prime factorization method. So let us take one number. Let us try to find out the LCM as well as HCF of these two numbers 2, 4. So 2 itself is a prime number, so we can write it directly. Next, coming to the 4, 4 is not a prime number, so try to do the prime factorization of this one. It is a small number only and we are very familiar with this one, so directly you can write it as 2 times 2. In case if any bigger number is there you are unable to do, means go with the prime factorization completely again as a rough part. So 2 times 2 is 4, so 2 2s are 4. Now circle which are common in these two, so here 2 is common. So now HCF will be, which is common, you need to write that one. So that is HCF. Then moving to the LCM, first write the number which is common into whatever extra is remaining, write that extra also. 2 times 2, it is 4. So the HCF is 2 and LCM is 4. Let us take one more example to make it more clear. I am taking the numbers 10, 15. So first let us try to write the prime factorization of these two numbers. 10, we know very well it is written as 5 2s are. 5 is a prime number, 2 is a prime number. Next 15 can be written as 5 3s are. Here also 5 is a prime number and 3 is a prime number. So our process is correct. Now circle which are common in these two. Here 5 is common, except 5 there are nothing common. So HCF will be 5. And moving to the LCM, first write the common number. 5 is common, so write it, into here extra 2 we have, so write it, into here extra 3 we have, write that also. So it will be 5 2s are 10, 10 3s are 30. So the LCM is 30 whereas HCF is 5. Let us move to one more problem. 48, 60. So first let us write the prime factorization of 48. 48 I am writing it as 8 into 6. In this case 8 is not a prime number, 6 is not a prime number, so this is not at all prime factorization. Further this 8 I am simplifying as 2 into 4. Here 2 is a prime number, okay, but 4 is not a prime number. This 4 again I am simplifying as 2 into 2. So now 8 can be written as 2 into 2 into 2. So here 8 I am writing it as 2 into 2 into 2 into, here I have one more number 6, right? Again 6 is also not a prime number, so that 6 I am writing it as 2 into 3. So finally 48 can be written as 2 into 2 into 2 into 2 into 3. If you feel that this process is lengthy or else it is confusing, directly you can go with normal prime factorization method. That is so easy than this one and no complications, no confusing also in that one. That is 48, if we take 48 is even number, so it will come in 2 table. 2 24 times 48. 24 is again even number, it comes in 2 table. 2 12s are 24. 12 is even number, it comes in 2 table. 2 6 are 12. 6 comes in 2 table. 2 3s are 6. As 3 itself is a prime number, so we can stop it there itself. Now we can write this as 48 equals to 2 times 2 times 2 times 2 times 3. Next, moving to the next number, that is 60. 60 equals to, I am doing the prime factorization here also for 60 again. So 60 equals to 2 table 60 30s are and 2 table 30 15s are. 15 is an odd number, so it won't come in 2 table. Now I am moving to the next prime number, that is 3. 3 5s are 15. As last number itself is a prime number, so we can stop the process here. So now 60 can be written as 2 times 2 times 3 times 5. Now first circle what are common in these all. So here 2 is common and one more 2 is also common and here 3 is also common. So the HCF will be now 2 is one time common, write it. 2 is again common, write it. Into 3 is also common, write that. So 2 into 2 into 3, that is 12. Now writing the LCM. First write the numbers which are common. 2 common, again 2 common, 3 common, into write all the extra numbers which are involved here. 2 is extra, write it, into again one more 2 is extra, write it, into here 5 is extra, write that 5 also. Now let us multiply these all, we will get the LCM of the given numbers. 2 2s are 4, 4 3s are 12, 12 2s are 24, 24 5s are 120, 120 2s are 240. So the LCM of 48 and 60 is 240, whereas HCF is 12. LCM of two numbers is 45 times their HCF. If one of the numbers is 225 and sum of their LCM and HCF is 1150, then find the other number. Let the first number in the question itself is given as 225. and second number is asking to find out, right? So let the another number be some x. Now according to the first condition, LCM of two numbers is 45 times their HCF. So that can be written as LCM equals to 45 times nothing but multiplication their HCF. So LCM equals to 45 into HCF. Next, sum of their LCM and HCF is 1150. So LCM plus HCF is given as 1150. Now LCM means 45 into HCF, right? So this LCM I will replace with 45 into HCF. Nothing but 45 HCF plus this HCF as it is equals 1150. 45 HCF plus HCF, it is 46 HCF, which equals 1150. Now I am taking this 46 to the right side, so it will be HCF equals to 1150 divided by 46. So the HCF is 25. Now HCF we got as 25, right? And we know that LCM equals to 45 into HCF. So LCM equals to 45 into HCF. So LCM will be now 45 into HCF is 25. Now I am not going to simplify this further because in the next step I can do cancellation. So there is no need of simplification here. Now we know the LCM into HCF equals product of two numbers. So LCM is 45 times 25 into HCF is 25 equals product of the two numbers. One number is given as 225, 225, and second number is unknown, so writing as x. Now taking 225 to the left side, 45 times 25 times 25 divided by 225, which is equals to x. Now let us do cancellation here. 45 ones are 45 fives are 5 ones are 5 fives are. So x is nothing but 25 times 5, 25 fives are, it is 125. So the second number is 125. If 2 log of x minus y equals 2 log 3 plus log x plus log y, then show that x square plus y square equals 11xy. So here he gave one equation. In this clearly it is visible that log is present, whereas in what we is asking to show, in that logarithm is not there. So our first intention is to removing logarithm from the given equation. So let us try to do that work now. So write the given equation as it is first. 2 log of x minus y equals 2 log 3 plus log x plus log y. So here the basic concept is that after simplifying completely, if we have something like log 2 equals to log x, something like this. Left side we have logarithm as well as right side also we have logarithm. So by comparing we can say that 2 is nothing but x. So here only one term should be there and the log should be completely to the end side, then only it is possible to compare and we can give some answer for that one. So for that reason what we will do is try to make the logarithm completely to the left side of the part. So here 2 log of x minus y is there, right? I will take this 2 to the power, so it will be log of x minus y whole square. We know a formula that if before the logarithm if any number is there means it will go as a power equals. Here also before the logarithm we have a number, now that will go as a power. So it will be like log 3 square plus I am writing the all remaining as it is log x plus log y. Now in the left side one already the logarithm is completely to the left side, so I need not to worry about the left side part. I am writing it completely as it is log of x minus y whole square equals to log 3 square is 9 plus log x as it is plus log y as it is. Now left side part as it is because already the left is completely to the end equals to right side part. If we observe log 9 plus log x plus log y, In logarithms, addition is there means we will do multiplication. So log 9 plus log x plus log y can be written as log, multiply all those numbers, 9 into x into y. So it is log 9xy. Now if we observe both the sides, here logarithm is completely to the left side of the part, as well as here also logarithm is completely to the left. Now we can compare these two. So by comparing, comparison means we will remove this logarithm, that much only, but we won't cancel that. You should not cancel like log cancel, that's completely wrong. You should not do that at all. So simply you need to write it by comparison. So x minus y whole square equals 9xy. Now x minus y whole square, I will expand it because in the equation he's asking us to show that x square plus y square. So that is the reason I'm expanding this. X minus y whole square is x square plus y square minus 2xy equals 9xy, as it is taking minus 2xy to the right side. So it will become plus 2xy, x square plus y square equals to 9xy plus 2xy, it is 11xy, hence proved.